We are going to produce this bath as well. And to do that, we are going to use the scale scenario. Okay. So again, in this case, the units for this icon will be scale English. So let's change the name here to Bathos Production and select Bathos Production. And now let's change the units here in the Units Manager to Scale English. So click on the Units Manager and change the units from Scale Metric to Scale English. Perfect. Okay, so now we already know what changes are going to occur when we change the units from metric to scale English. So I don't need to go through these details. We can simply click OK. Okay. So once we do that, the next step is to bring the whole fluid, the whole contents of this Bathos reservoir. We want to study this. This is what we spend time entering all of these analyses, analyzing and saturating this reservoir with the specific mineral. So these are the contents that I want to bring to produce. So I am going to go to Type and select Whole Fluid. Another option you have here is that you simply can just click on the Bathos reservoir and transfer it directly into the inlets. And it will do it automatically for you, everything. The whole fluid, Bathos reservoir, and the automatic flow. Again, I just simply select it and then drag it into the inlet tab. Okay. What else should talk about here? So this is all. This is all what we need to do in inlets. And the next step is to set up the conditions, right? We have different locations during production, and we just need to enter the locations with the specific temperatures and pressure. Okay, so we can start entering the names here. I usually provide with the training, I provide an Excel spreadsheet where I simply can just copy and paste the values so that we don't have to enter every time the information. But I don't know, I'm not positive if everyone has access to that Excel spreadsheet. So I will just type with you so that everyone, if the people that doesn't have this Excel spreadsheet, then we can just simply enter this and we can all be in the same page. But just let me know. So because I provide that Excel spreadsheet so that you can also go back and check on the examples and you don't have to type every time that you want to do the examples. You can simply copy and paste from the Excel spreadsheet for all the examples we have covered so far. So, okay, so we are going to type. And the first location that we are going to create is the original reservoir. In this case, I wrote the name, original reservoir, and I entered this temperature and the pressure. That will be at reservoir conditions. So again, it starts creating my nodes down here. And the next location is just to recreate the reservoir. This is the original conditions of the reservoir, and now we are going to recreate the current reservoir, like as of today. What has changed? The temperature remains the same, but the pressure has decreased to 160 bar G. So we want to change. We want to see the changes of that pressure drop. Then we also have flowing reservoir. And again, temperature remains the same, but now we have a drop in the pressure to 150, okay? And next we have the bottom hole. 200, and the pressure reduces to 147. Now we have a location, it's called 2,600 feet, so we put it here. And 1 second, I have someone calling me. I need to close this. 200, and then we enter the value here, 190. 190, and then 206 will be 166. Excuse me, give me 1 second. Someone is trying to call directly to my computer and I don't know how to stop that. Incoming call. Let's close this. Turn off. Ignore. Okay, I think I closed it. I'm going to just quit this and I should not be bothered. Okay, so now for the next location is 1,300 feet, and we have that the temperature goes down to 180 and the pressure goes significantly down to 80. Then we have the next location is the wellhead, and in the wellhead we have 170 and 54 bar G. We have two more locations. We have the flow line, and the flow line is at 150 and 33.5 bar G. And the separator is at 140 Fahrenheit and 9.3 bar G. Okay. Save. And I hope that just put everything here. I don't know if you can all see. Okay. Let me know if everyone is up, like enter all of this information, if everyone has entered everything and I'm not going too fast.
Could you scroll down to see the values for the separator?
Sure. There it goes. Okay. So the diagram down here is basically what it's telling us is that it's indicating that all the material is being sent through. Okay, so we have the same mass that is the same mass is being used at each location. We are not seeing any mass loss, separations, solids dropping, nothing. We are assuming that the same mass is traveling along all the production. Okay, it's one thing I want to make sure that we are conserving mass in here. Okay, so once we are done with this part, the next step is, and we can never forget this standard, because sometimes I always forget, and then I'm like, why am I seeing different? Why am I not saturating solids or precipitating solids? And it's because I always forget this step. So let's go to the solids and check on the standard, and then let's go ahead and calculate. Okay, so that will take us to the next part, that will be analyzing the results. Okay, so based on where we spend so long trying to understand how to recreate that Bathos reservoir, and this is really what we need. We want the plot. We want to know what's happening, which solids we are going to precipitate out, and how much, and at which location. Okay, so this plot again is the default plot, the dominant prescale tendency values versus the locations. And again, we are looking for solids that are above the saturation ratio of 1. Below 1, that means the solids will be undersaturated. We are interested in everything above 1. Okay, so the solid that seems to be causing issues here is the calcite, this red line that you see here. Okay, so it's the one that is super saturated, at least at the current reservoir conditions, the flow in reservoir, and the bottom hole. Once you go to the next location, 2,600 feet, that supersaturation value, the saturation value is not longer above 1, and it starts to decrease until we reach the separator again, where it reaches a value of 1.16, okay, at the separator conditions. So again, if we want to see that these are the dominant solids, and if we want to see the amount of solids, you can click on View Data and go to Variables and check on the solids and see that the software is saying, okay, the calcite. Calcite is the one that is being precipitated out, and you want to know how much. And these are the values in milligrams per liter. So you want to compare the pre-scaling tendency, or you want to have these pre-scaling tendency values and how much of that solid is being is coming out. So you'll see the maximum amount of solids that are coming out from solution is it happens at the bottom hole, 36, almost 37 milligrams per liter. And this is how much is precipitating out of the fluid at the separator. Okay. What else can we analyze from these results? Okay. We can say we can analyze something here that I did not cover last time. This is simply the plot, right? We are seeing the information that the software decided to show us. But there is more information than this. So another set of results that we can check is this report table, or this report tab here for the bagasse production. So we go to the report tab, and in here you will see a significant amount of tables, a lot of them. You will see the tables that we have, that I have talked about before. You will see them for every single location. So we have it for the original reservoir, all the tables, we have it for the current reservoir. So what's happening, what is the composition of the brine at the specific location, the oil composition at the specific location, everything. So what I want you to do is try to scroll down in this report, and let's look for the results at the separator conditions. Okay, let's look for those. That's 2000, it's very long. So as we scroll down, this is the wellhead, it's almost the last one, right? Separator. Okay, so it's like 2/3 down this scroll down bar. So we have arrived to the separator conditions. So again, we have stream properties. These are the separator conditions and how much mass we have there in pounds per day. For the phase properties, okay. So we need to confirm, yes, at the separator conditions, we did have, well, we entered a liquid phase, a vapor phase, and an organic or oil phase. So the software is predicting that yes, we do have those phases. We have the liquid phase, which is the brine, and it's saying that yes, we are producing it at 850 barrels per day. So the software is predicting this amount, and that was actually the same amount that was measured at the separator conditions. So we are good. The mass balance, we are having mass balance. Okay. For the organic phase, for the oil phase, okay, the software is predicting 2,214 standard barrels per day versus the 2,200 standard barrels per day that we measured, or that were entered, that were measured at the separator. Okay. Again, this value is not far. It's not that far from what was measured. So the software is also doing a good job here of calculating the amount of oil that was measured at separator conditions. Now we can also go to the gas phase. The gas phase, if you remember when we entered the values at Bathos Reservoir, we entered 300,000 standard cubic meters that were being produced. And the software is saying that 275,000 standard cubic meters is what is being produced according to this. At separator, the software predicts 275,000 standard cubic meters. Oh no, this is not standard cubic. This is standard cubic feet per day. So we are off by around 8% here when it comes to the mass balance of this vapor phase, right? And I want to point out that remember that at the very beginning, when we were adding the gas analysis, okay, we made the assumption for the gas phase. We assumed that it was 100% methane, okay? So if you scroll down here in this under the separator, if you scroll down and look for the oil and gas composition table, okay, you can see that the software is computing the composition of the oil, right? This will be the composition of the oil that the software is calculating, and is also calculating the composition of the gas. Okay, so you see here that the gas, this will be all the components of the gas. We are having all of these pseudo components as part of the gas. In the gas, we are also having, the software is saying that in the gas component, in the gas phase, we don't have 100% 100% mole percent of methane. We are having 86 mole percent, right? That this gas also contains some CO2 in this composition. That this gas also has some water content, 1.95% of water content. And that it has all of these other pseudo components in a very minimum amount, but still we have some of these pseudo components in the gas phase. Okay, so this table here is giving you an idea of the composition of the gas if you are not given gas composition in your study. So now the reason why we are not matching this mass here is because since now we know that we should have accounted for some water in that gas and that we should have accounted for some CO2 and some other components that we are missing, that we were missing in the original gas analysis. Okay, so that's the story I wanted to tell you about this specific Bathos production calculation. Are there any questions about this? Okay, let me see the chat. Okay, cool. Miss is clear. Clear as mud, like my colleague likes to say. I hope it's really clear. Okay, so now in here, I have this object library here. You can always close it. We are not going to use it. So it's kind of occupying real estate here. So let's just close on the X. And let's save this. And we're going to do a last calculation. Just again, the last calculation for this is going to be the scale counter. And this scale counter is going to help us to basically have integrated operating windows. Basically, based on the information that we have with the water analysis and the gas analysis and oil analysis, and now that we have recreated this reservoir, what are the ideal operating conditions to avoid scaling? Okay, so that's what we're going to do. We're going to create a map that is going to tell us, or is going to give us an idea of the best operating conditions when we are producing this well. So double click on the scale scenario and change the name to Bathos counter. And this one is going to be really quickly. We already are familiar with this. And we're going to bring the contents of Bathos Reservoir to this calculation. So again, you can either select here under type, whole fluid, Bathos Reservoir, and it will be the automatic flow. And or you can simply select it and drag it to the inlet tab. And that will bring everything here for you. Okay. The units of this Bathos contour, seems that is the metric scale. You have two options. You can just continue working in metric or select the Bathos contour and change it to scale English. I'm going to change it to scale English so that we can use the units for this specific Bathos scenario. Okay, the next step is to go to conditions. We are going to enter the range of temperature and the range of pressure. The minimum temperature of operation for this reservoir, for this production, is 140 to 200 is the maximum, 200. And we are going to say that we're going to study this every 4 increments. Temperature is in Fahrenheit. So if you didn't change the units, you have a second chance here to change the units from Celsius to Fahrenheit. And then the pressure range, I don't want it in log scale. I want the minimum pressure to be 10 bar G and the maximum pressure to be 150 bar G. Again, if we didn't change the units, make sure that you can change here the pressure to bar G. And for we're going to study this every 10 increments. You can make this more refined if you want, but this is again for demonstration purposes, and it just takes, the more refined that you get the plot, the more time it takes to compute. So I'm going to make it very coarse. And the last step, solid. Make sure that you have selected your solids. Now, I don't want to calculate that. Well, actually, what time is it? I say what we can do is let's click on the calculate button and we can go for a break when we can be back in 6 minutes. Well, let's take a 10-minute break. I'll give a little bit longer of a break. So I will meet you at the top of the hour so that we can continue with our last object, which is, I realize I made a mistake and maybe I instructed you to do to follow the same mistake, and I apologize. It's not a big deal though. It doesn't change the results, it just changed how the plot is being shown. Okay, I just wait to see if everyone is back. Please let me know. You can state your name or write on the chat that you're here. Then we can continue. Okay, great. Okay, have some people here. Okay, so one of the things that I don't know why by default in this selection, when you're doing the temperature and pressure range, for some reason we always have this log scale as the one by default. In some cases it's useful because you're really analyzing a wide range of temperatures and pressures, but in some cases I just want a linear scale. So in this case I forgot to unselect the logarithm scale. So that's the reason why you see this scale here in the pressure axis. If you didn't select it, good. It should look like this. The plot should look a linear scale and a linear scale for both pressure and temperature. But again, it should not affect the results in any manner. It just it's just that is how it is being plotted. Okay, so what is this plot telling us? I mentioned before that this is the excess solute value here, and the plot is telling us how much of it is being, how much of it you have. And this takes into account all the potential solids that are, or the potential scales that are being formed. However, last time I did not tell you how you can manipulate this plot. Let's say you don't want to see this total solid concentration. You want to see the calcite, specifically the calcite scale, or you want to see pH values, or you want to see CO2 concentrations, how they are changing as you change pressure and temperature. Okay, so there are several options, or there are ways to change this. One of them is the variables. You can go to variables, and again, you will have access to all the potential categories, all the potential variables or values that have been calculated in the software. Okay, so in this case, let's say we want to see the amount of calcite that can be formed at a specific set of temperature and pressure. So you select the calcite, let's say, and then use this arrow here to overwrite this total solid concentration. This is going to be my new contour variable. And then click apply to see if there are changes, right? You see that there were no changes, because the only solid that is being formed, it seems, is for this specific well, is the calcite. Calcite is the main scaling risk for this production. Okay, let's say that you want to study the pH of this specific fluid. So you can go to additional stream parameters, the one at the top, and look for pH. Okay, then you select the pH and then click apply. Okay, so in this case, everything is green, and it doesn't mean that the pH is being held constant at all temperatures and pressures. What happens is that the software uses by default this range of pH that you see here, 0 to 14, right? And the pH is more or less going, or is the pH that is being predicted probably is going to be around 7, most likely. I don't know. But we can fix this. How do we fix this? We go to options, and then we go to contour. And either we change the values 0 to 14 from, I don't know, 5 to 7, something like that. Or we can just tell the software, identify my minimum pH, my maximum pH, and then click apply, right? So this is the plot. This is how the plot should look. Let me click OK here just to exit this. And the pH is ranging from 5.73 to 6.13. Okay, so this means that maybe this we could find out. We could find out what could be contributing to this pH. Is it the CO2 concentration? We could see if that is what is causing those changes in pH. But we can see that at high pressures and at low temperatures is where we have the highest or the lowest pH, right? The lowest pH. And at high temperatures and at low pressures is where we have our highest pH. And this pH still is 6, is below neutral. So it's not like it's going, we definitely are having some composition of some type of molecule here, could be CO2. We can find out that is contributing to lowering the pH. Okay, so that's what we can do next. We can go to variables, and let's say we want to find out what's happening in the liquid one. Liquid one stands for the brine, the aqueous phase, and we look for the molecular CO2. I want to see if molecular CO2 is having an impact on this pH value. So Again, I go to liquid 1, scroll down and look for my CO2 liquid 1. Then put in the control variable and I click apply. And we can see that sure enough, at high pressures and low temperatures is where I have my highest concentration of CO2, right? And at low pressures and high temperatures is where I have my low concentration of CO2. And this kind of makes sense because as we increase the pressure, we are forcing the CO2 to remain in the liquid phase. And this causes the speciation reaction to go from CO2 to bicarbonate and that and H+. And that H+ is the one that is causing the change in the pH. And same here. So if we have higher temperature and low pressure, it means that the CO2 leaves the brine or the liquid phase. And then as a result, it's not going to affect the pH as much. This is useful, for example, if you want to know how corrosive this production fluid is. So with a pH range, you can have an idea of how aggressive the solution is for your pipe. Okay, so that is regarding how you can manipulate the plot, the contour plot. And you can plot in here all the variables that we give to you. So you have an idea of what is happening at the whole range of pressure and temperature. Just wanted to show you that you have that option.